Hello there, and welcome to the Sleepless Astronaut channel. I'm so glad you're here tonight. You know, sometimes the most profound questions are the ones we rarely stop to ask. Questions about things so fundamental, so deeply woven into our existence, that we simply take them for granted. We move through life accepting certain things as obvious, as givens, without ever pausing to wonder whether they're truly what they seem. Tonight, we're going to explore two of these mysteries together. Two things that seem so basic, so simple, so everyday that we almost never question them. And yet, when we look closely, when we really think about what they are, we discover depths and strangeness that scientists are still trying to fully understand. Tonight, we're going to think about space and time. What are they, really? Where do they come from? Are they fundamental aspects of reality, or are they something else entirely? Something stranger and more elusive than we've ever imagined? Are they even real in the way we think they are, or could they be illusions, emergent properties of something deeper? Now, before you worry that this will be complicated or difficult, let me assure you it won't be. We're not going to dive into complex mathematics or get lost in technical jargon. There won't be equations or calculations or anything that requires you to think hard or concentrate intensely. Instead, we're going to explore these ideas gently, peacefully, using simple thoughts and everyday experiences as our guide. And as we explore, you're going to relax deeper and deeper, letting these cosmic mysteries carry you softly toward sleep. So settle in now. Get comfortable wherever you are. Adjust your pillow if you need to. Pull your blanket a little closer. Feel the softness of the surface beneath you, supporting your body completely. Take a slow, deep breath and feel your chest rising and falling. Notice how peaceful you already feel, how ready you are to let the day fade away, to release all the small concerns and worries that have occupied your mind. Tonight, your mind is going to wander through some of the deepest questions in all of science. Questions that have puzzled philosophers for thousands of years, and that scientists are still working to answer today. But as your mind wanders through these questions, your body is going to rest, preparing for sleep, sinking deeper into relaxation with every breath. Let your eyes close if they haven't already. There's no need to keep them open. Just let them gently close and rest. Let your breathing find its natural rhythm, whatever feels most comfortable and easy. Slow and deep or quick and shallow, whatever your body wants right now. There's no right or wrong way. Just breathe naturally and let yourself relax. There's nowhere to be tonight. Nothing to do. No tasks waiting, no obligations pressing. Just this moment, this quiet time, this gentle exploration of ideas. Just listen, drift, and let these thoughts flow through your mind like water flowing through a peaceful stream, clear and calm and unhurried. What is space? What is time? Let's begin by thinking about how we experience them every day in the most ordinary moments of our lives. Space seems simple enough, doesn't it? It's the emptiness around you, the distance between things. The room you're in right now has space in it. There's space between you and the walls, space between the furniture, space between your hand and your face if you hold your hand up. Space is what separates objects, what allows them to be in different places. When you look around a room during the day, you see objects separated by space. The lamp is over there, several feet away. The wall is a certain distance in that direction. The door is somewhere else. Space is what's between all these things, the invisible medium, that allows for separation and distance. And you can move through space. You can walk from one side of a room to the other, crossing the space between. You can travel across town, across the country, across the world, moving through space to get from one location to another. Space seems like a container, a vast empty box that holds everything, unchanging and always there, the same for everyone. This is how we experience space in our everyday lives, and it seems so obvious, so self-evident, that we rarely question it. Space is just there. It's the emptiness, the background, the stage on which life plays out. And what about time? Time seems equally straightforward, equally obvious. Time flows. It moves from past to future, carrying us along whether we want to go or not. You can feel it passing right now. Seconds are ticking by, minutes are accumulating. Each moment gives way to the next in an endless procession, from what was to what will be. We remember the past, things that happened earlier today, yesterday, last week, years ago. Those moments are gone now, vanished into the past, accessible only through memory. We experience the present, this very moment, this instant that's always right now, always fleeting, always slipping away into the past, even as we notice it. And we anticipate the future, thinking about what might happen next, tomorrow, next week, imagining possibilities that haven't occurred yet. Time feels like a river flowing in one direction, carrying everything along with it. We can't stop time, can't reverse it, can't do anything except move forward with it at a steady pace. 1 second per second, 1 minute per minute, time passes and we pass through it. These seem like such obvious everyday experiences that we rarely question them. Space and time are just part of reality, fundamental aspects of existence, as basic as anything can be. But are they really what they seem? Are they truly separate things, a container and a river, space holding things and time carrying things forward? Or is something stranger, something more subtle and complex, going on beneath the surface of these everyday experiences? Take a moment to really think about this, not to strain or struggle with the question, but just to let it rest in your mind gently. You're lying in your bed right now, occupying a particular position in space. You're in a specific location, and that location can be described by coordinates, by directions, by distances from other things. Here, right here, is where you are in space, and you're experiencing this particular moment in time, this present instant as it unfolds, right now. This exact now that's happening as you hear these words, as you breathe in and out, as you rest in your bed. This is when you are in time. But what does that really mean? What is this space you're occupying? Is it a thing, a substance, something real and tangible even though you can't see or touch it? Or is it just nothingness, absence, the lack of anything else? And what is this time you're experiencing? Is it flowing like a river, or are you moving through it, or is something else entirely happening? Your breathing is slow now, deep and regular and peaceful. Feel how relaxed you are, how comfortable your body feels. Your muscles are loose and heavy. Your mind is calm and quiet. We're about to explore some ideas that might seem strange at first, ideas that challenge our everyday understanding of reality. But don't worry about understanding everything perfectly. Don't try to grasp every detail or remember every point. Just let the thoughts flow through you, washing over you like gentle waves, absorbing what resonates and releasing the rest. For most of human history, people thought space and time were exactly what they seemed to be in everyday experience. Space was the stage on which the universe played out, a vast three-dimensional container that held everything unchanging and absolute, the same everywhere and for everyone. Time was the universal clock, ticking away at the same rate throughout the cosmos, past and future flowing identically for all observers, no matter where they were or what they were doing. This view seemed to work perfectly well. It matched everyday experience. It matched common sense. It made intuitive sense and allowed people to navigate the world, to build things, to understand motion and change. And for centuries, for thousands of years, this understanding was considered obviously correct, the only sensible way to think about space and time. Philosophers debated the details. Some thought space and time existed independently, that they were real things in their own right, even if the universe were empty. Others thought space and time were just relationships between objects, that they had no independent existence and would be meaningless in an empty universe. But everyone agreed on the basic picture. Space was space, a three-dimensional container. Time was time, a one-dimensional flow. They were separate, distinct, and absolute. But then, in the early years of the 20th century, something changed. A young scientist working in a patent office began thinking deeply about the nature of light, about how it travels through space, about what observers in different situations would see. And through these thoughts, through careful reasoning and bold intuition, he discovered something remarkable, something that would completely transform our understanding of space and time and shake the foundations of physics. That scientist was Albert Einstein, and his discovery was that space and time are not what we thought they were. They're not separate. They're not absolute. They're not the same for everyone. Instead, they're flexible, relative, intimately connected, woven together into something more complex and strange than anyone had imagined. Einstein's journey toward this discovery began with a simple observation about light, an observation that had puzzled scientists for years. Light travels. It's not instantaneous. When you flip a switch, there's a tiny delay, far too small to notice in everyday life, between when the switch is flipped and when light reaches your eye from the bulb. When you look up at the night sky, you're seeing light that has traveled from distant stars, sometimes for years or centuries or even millions of years, crossing the vast emptiness of space to finally reach your eyes. And light travels at a specific speed, not infinitely fast, but at a finite, measurable velocity. Scientists had determined this speed through careful experiments, and it turned out to be very fast indeed. Light travels fast enough to circle the Earth more than 7 times in a single second. Fast enough to reach the moon in just over a second. Fast enough to travel from the sun to Earth in about 8 minutes. Fast enough to cross the entire solar system from the sun to the outermost planets in just hours. This speed seemed extraordinarily fast by human standards, faster than anything we experience in everyday life. But it was still finite, still limited. Light didn't travel infinitely fast. It had a specific speed, a particular rate at which it moved through space. Now, here's where things get interesting. Here's where Einstein noticed something strange, something that didn't quite make sense according to the old understanding of space and time. When scientists measured the speed of light, they always got the same answer. No matter how they did the experiment, no matter what conditions they tested, the speed of light was always the same. and this by itself wasn't particularly surprising. Many things have consistent, predictable speeds. But here's the weird part. The speed of light was the same no matter how the observer was moving. This shouldn't have made sense according to the old physics, according to the way people thought speeds should add up. Let me explain what I mean, because this is genuinely strange, and it's the key to understanding everything that follows. This is the puzzle that Einstein solved, and solving it required rethinking space and time themselves. Imagine you're standing still on the ground, and someone throws a ball toward you. You measure how fast the ball is moving. Let's say it's moving at a certain speed, maybe 20 miles per hour. Now imagine you're in a car driving toward the person throwing the ball at, say, 30 miles per hour. They throw the ball at the same speed as before, 20 miles per hour. But because you're moving toward the ball, it appears to be moving faster relative to you. The speeds add together. The ball appears to be coming at you at 50 miles per hour, 20 from its own motion, plus 30 from your motion. This is how speeds normally work in everyday life. They add together or subtract depending on how you're moving. If you're moving towards something, it appears to be coming at you faster. If you're moving away from something, it appears to be moving slower. Simple, intuitive, obvious. Now imagine the same thing with light instead of a ball. Someone shines a flashlight toward you. You measure how fast the light is moving. Then you get in a car and drive toward the flashlight at high speed. You'd expect the light to be coming at you faster now, right? The speed of the light plus the speed of your car, just like with the ball. But that's not what happens. You measured the light, and it's traveling at exactly the same speed as before, not faster. The same speed you measured when you were standing still. Now imagine you turn around and drive away from the flashlight at high speed. You'd expect the light to be moving slower relative to you now, catching up to you more gradually because you're running away from it. But again, you measure the light, and it's the same speed. Always the same speed, no matter what you do, no matter how fast you're moving, no matter which direction you're going. This seems impossible. It seems to violate common sense and the basic rules of how speeds should work. But it's true. It's been verified by countless experiments over more than a century. Light always travels at the same speed for every observer, regardless of how they're moving. Take a slow breath now. Notice how peaceful you feel, how your mind is engaged but not struggling, interested but not tense. These ideas might seem strange, might challenge your intuition, but that's okay. You don't need to fully grasp everything. Just let the thoughts flow through you, and trust that the strangeness will start to make sense as we go deeper. Einstein realized that if light always travels at the same speed for everyone, then something else had to be flexible. Something else had to change to make this work mathematically, to make the universe consistent. And the only things that could change, the only things with any freedom in the equations, were space and time themselves. Think about it this way. Speed is distance divided by time. How far something travels, divided by how long it takes to travel that distance. If the speed of light is always the same, absolutely constant for every observer, but different observers are moving in different ways, then distance and time must be different for different observers. They must be flexible, adjustable, relative rather than absolute. Space must be different for different observers. Time must be different for different observers. And this was Einstein's great insight, his revolutionary discovery that changed physics forever. Space and time are not absolute. They're not universal constants that are the same for everyone. They're relative, flexible, dependent on how you're moving, where you are, what you're doing. Two observers moving at different speeds will measure different distances between the same 2 points in space. They'll measure different amounts of time passing between the same 2 events. And both of them will be right because there is no absolute space, no absolute time. There's only your space, your time, my space, my time, each dependent on our particular situations. This idea is called relativity, and when Einstein first proposed it in the early 1900s, it completely overturned the way scientists understood the universe. It was shocking, counterintuitive, difficult to accept, but it was also undeniably correct, supported by experiments and observations, confirmed again and again by every test scientists could devise. Let me give you an example that makes this more concrete, more vivid, and easier to imagine. Suppose you have a twin, someone who's exactly the same age as you, born at the same moment. And your twin decides to become an astronaut and boards a spaceship capable of traveling very fast, close to the speed of light. The ship takes off from Earth, accelerates to enormous speed, travels across the galaxy for what feels to your twin like a few years, then turns around and comes back, decelerating and landing back on Earth. The whole journey, from your twin's perspective, takes maybe 5 years. 5 years of traveling through space, seeing stars slip past, experiencing time in the usual way, 1 second per second, everything feeling normal. But when the ship lands and your twin steps out, you've aged not 5 years, but maybe 50 years. Decades have passed for you, while only a few years passed for your twin. You're now much older than your twin, even though you started out the same age. This isn't science fiction or fantasy. This is real physics, a genuine consequence of relativity. Time really does pass more slowly for someone moving very fast compared to someone moving slowly or standing still. Not because of some trick or illusion, not because clocks malfunction or observers make mistakes, but because time genuinely, truly flows at different rates depending on how fast you're moving. The effect is tiny at everyday speeds, far too small to notice in normal life. When you drive in a car or fly in an airplane, time passes slightly more slowly for you than for someone on the ground, but the difference is minuscule, measured in tiny fractions of a second even after hours of travel. But at very high speeds approaching the speed of light, the effect becomes dramatic. Time slows down significantly. Years can pass for a stationary observer, while only days or months pass for someone moving very fast. This time dilation, this slowing down of time with motion, has been confirmed in laboratories using particles that decay after a certain amount of time. When these particles are accelerated to high speeds, they last longer before decaying, living longer than they should according to their own internal clocks, because time is passing more slowly for them. It's been confirmed using precise clocks flown on airplanes, clocks that tick slightly slower than identical clocks left on the ground, exactly as relativity predicts. It's been confirmed using satellites orbiting Earth at high speeds, satellites that experience time slightly differently than we do on the surface, and whose clocks have to be adjusted to account for this difference. Time is not absolute. Time is not the same for everyone. Time is relative, flexible, dependent on motion. Your breathing is so slow now, so peaceful and regular and natural. Feel how deeply relaxed you are, how comfortable your body feels sinking into the bed. Your muscles are loose and heavy. Your mind is calm, drifting gently through these ideas without strain or effort. We're exploring the nature of reality, the flexibility of time itself, but you're not working hard to understand. You're just letting the thoughts flow through you, absorbing what resonates, releasing the rest. And it's not only motion that affects time, gravity does too. This was Einstein's next great insight, his extension of relativity beyond motion to include gravity as well. Einstein realized that mass, that matter and energy don't just exist in space. They actually warp and curve the fabric of space itself. And in doing so, they also curve time. Imagine space as a stretched rubber sheet, flat and smooth. If you place a heavy ball on the sheet, the weight of the ball creates a depression, a curve, a dip in the sheet. The sheet is no longer flat. It's bent, curved around the ball. If you place a smaller, lighter ball nearby on the sheet, it will roll toward the heavy ball, not because the heavy ball is pulling it in some mysterious way, but because the sheet itself is curved, and the natural path across a curved surface leads toward the depression. This is how gravity works according to Einstein. The sun, being massive, curves the space around it. Earth, moving through this curved space, follows the natural path through the curve, which happens to be a roughly circular orbit around the sun. We experience this as gravity pulling Earth toward the sun, keeping us in orbit, but really Earth is just following the shape of space itself, moving along the natural path through curved spacetime. And just as mass curves space, bending it into valleys and hills, it also curves time. Time passes at different rates depending on how deep you are in a gravitational field, how close you are to massive objects. Near a massive object, deep in the gravitational well it creates, time passes more slowly than it does far away from mass. The effect is usually small, barely noticeable, but it's real, and it's been measured. If you're standing at the base of a mountain, time passes slightly more slowly for you than it does for someone at the peak, because you're closer to the center of Earth, deeper in Earth's gravitational field. The difference is tiny, far too small to notice in everyday life, but with precise enough clocks, it can be measured. If you could stand on the surface of the sun, which you can't because you'd be vaporized instantly, but if you could, time would pass more slowly for you than it does for someone on Earth, because the sun is more massive than Earth and its gravity is stronger. If you could somehow survive near a neutron star, an incredibly dense collapsed star where a huge amount of mass is compressed into a tiny space, creating intense gravity, time would pass much more slowly for you. You might experience a few minutes while years passed for someone far away in space, far from any gravitational influence. And near a black hole where gravity reaches its most extreme, where space-time is curved so severely that it almost folds back on itself, time nearly stops. An observer falling toward a black hole would experience time, normally from their own perspective, ticking away second by second in the usual way. But to someone watching from far away, from a safe distance outside the black hole's influence, the falling observer would appear to slow down, moving slower and slower as they approach the black hole's boundary, eventually seeming to freeze in place, hovering forever at the edge, though from their own perspective they crossed the boundary and fell inward without hesitation. This isn't a trick of light or a limitation of observation. This is the genuine behavior of time in extremely curved spacetime. Time really does pass at different rates depending on where you are in a gravitational field. Take another slow breath. Notice how calm you feel, how peaceful. Your body is completely relaxed, now heavy and still. Your mind is drifting gently through these cosmic ideas, these strange properties of time and space, but you're not straining to understand every detail. You're just letting it all wash over you like gentle waves on a shore. Einstein didn't just discover that space and time are flexible, that they change with motion and gravity. He discovered something even more profound, something that changed the entire way physicists think about reality. Space and time are not separate things. They're not independent aspects of the universe that happen to exist alongside each other. They're woven together into a single unified entity, a fabric that has both spatial and temporal dimensions. And this fabric is what we call space-time. Before Einstein, people thought of space as a three-dimensional box. You could move left or right, that's one dimension. You could move forward or backward, that's a second dimension. You could move up or down, that's a third dimension. 3 dimensions of space, all perpendicular to each other, forming a 3-dimensional grid that extended infinitely in all directions. And time was something separate, flowing alongside space, but not connected to it. Time was the universal clock, ticking away independently, the same for everyone, unaffected by space or motion or gravity. But Einstein showed that this separation is an illusion, a consequence of our limited everyday experience where speeds are slow and gravity is weak. When you look more carefully, when you account for motion and gravity, when you follow the mathematics wherever it leads, you discover that space and time are intimately connected, merged together so thoroughly that you can't truly separate them. Space and time are aspects of a single 4-dimensional fabric. 3 dimensions of space, 1 dimension of time, all woven together, all influencing each other, all part of the same underlying reality. When you move through space, you're also moving through time. The faster you move through space, the slower you move through time, and vice versa. When you stand still in space, you're moving through time at the maximum rate, 1 second per second. When you move very fast through space, you move more slowly through time, experiencing less time for a given distance traveled. Everything in the universe is always moving through space-time at a constant rate, tracing paths through this 4-dimensional fabric. What we experience as motion through space and passage through time are really just different aspects of motion through space-time. And this fabric, this space-time, is not rigid or unchanging. It's dynamic, flexible, responsive. It curves around massive objects, creating the effect we call gravity. It can ripple and vibrate when masses accelerate or collide. It expands as the universe grows. Space-time is alive in a sense, constantly shifting and changing in response to the matter and energy within it. Picture this in your mind as vividly as you can without strain or effort. You're not just sitting in space with time flowing past you like a river. You're embedded in space-time, a 4-dimensional fabric that extends in all directions, including the direction we call time. You're moving through this fabric right now, tracing a path from past to future, and the fabric itself is curving gently in response to the mass of Earth beneath you, the sun nearby in space, the galaxy surrounding you. Every object in the universe, from the tiniest particle to the largest galaxy, exists within spacetime and moves through spacetime and influences the shape of spacetime through its mass and energy. Spacetime is the stage on which physics plays out, but it's also an active participant, shaped by what happens on it, influencing what can happen next. This might sound abstract, purely theoretical, the kind of thing that only matters in thought experiments or extreme situations. But spacetime and its properties have very real, very practical consequences that affect your everyday life. In fact, you rely on Einstein's understanding of spacetime every single time you use a navigation app on your phone to get directions or find your location. Here's how it works. Satellites orbit Earth high above the surface, moving at considerable speed relative to the ground. Each satellite carries extremely precise atomic clocks that measure time with incredible accuracy, losing less than a second over millions of years. These satellites constantly broadcast signals that include the time according to their onboard clocks. Your phone receives signals from multiple satellites, compares the times in those signals, and uses the differences to calculate distances to each satellite. With distances to several satellites known, your phone can triangulate your position on Earth's surface with remarkable precision, often accurate to within a few feet. But here's the key point. The satellites are moving fast, orbiting Earth at thousands of miles per hour. According to relativity, time passes more slowly for them because of their motion. At the same time, they're higher up than you are, farther from Earth's center, in a weaker gravitational field. According to relativity, time passes more quickly for them because of this reduced gravity. These two effects work in opposite directions. The motion makes their clocks run slower. The altitude makes their clocks run faster, but the effects don't cancel out perfectly. One is slightly larger than the other, and the result is that time passes at a measurably different rate for the satellites than it does for you on the ground. If the satellites didn't account for relativity, if they assumed time was absolute and flowed at the same rate everywhere for everyone, their timing would be wrong. And wrong timing means wrong distances, and wrong distances mean wrong positions. Within a single day, the errors would accumulate to several miles. Your navigation app would tell you you're in the wrong place, sometimes miles away from where you actually are, making the system essentially useless. But the satellites do account for relativity. Engineers program them to adjust their clocks based on Einstein's equations, compensating for the fact that time passes differently for them than it does for us on the surface. They correct for both the motion effect and the gravity effect, ensuring their clocks stay synchronized with ground-based time, despite the relativistic differences. And because of these adjustments, because engineers took Einstein's discoveries about flexible space and time seriously and built them into the system, your navigation works perfectly. It guides you accurately to your destination, lets you find your location on a map, helps you navigate unfamiliar places. Every time you get directions from your phone, every time you check your location, you're using Einstein's relativity. You're relying on the fact that space and time are flexible, that they curve and stretch in the presence of mass and motion. It's a beautiful example of how even the strangest, most counterintuitive ideas in science, ideas that seem purely theoretical and divorced from everyday experience, can have practical applications that we use every single day without even thinking about it. Your breathing is barely perceptible now, so slow and gentle and peaceful. You're floating on the very edge of sleep, drifting in that soft space between waking and dreaming. We've covered a lot of ground tonight, learned about how time slows down with motion, how gravity curves space and time, how space and time are woven together into space-time. And we're going to explore even more, going deeper into these mysteries. But first, just rest here for a moment. Just breathe. Just let yourself sink a little deeper into the comfort of your bed. Let's think about what all this means for your experience right now, in this exact moment, lying peacefully in your bed, preparing for sleep. You feel like you're sitting still, not moving through space, just resting peacefully in one place. But in reality, you're moving through space-time at an incredible rate, tracing a path through the four-dimensional fabric that includes both space and time. You're always moving through time, of course. Second by second, moment by moment, you're tracing your path from past to future. And this motion through time is constant and inevitable. You can't stop moving through time any more than you could stop your heart from beating or your lungs from breathing. But you're also moving through space in ways you don't normally think about. Earth is spinning on its axis, rotating once every day, carrying you around at hundreds of miles per hour, even though you feel perfectly still. If you're near the equator, you're moving even faster because the Earth is wider there, and you have farther to go in each rotation. And Earth is orbiting the Sun, traveling through space at tens of thousands of miles per hour, completing one full orbit every year. This motion is smooth and constant, so you don't feel it, but it's there, carrying you through space along with the entire planet. And the Sun itself is orbiting the center of the Milky Way galaxy, moving through space at hundreds of thousands of miles per hour, taking the solar system and all the planets along with it. The Sun orbits the galaxy once every couple 100 million years, so you'll never complete even a fraction of one orbit in your lifetime. But you're moving through space with the Sun nonetheless. And the galaxy itself is moving through space relative to other galaxies, drifting through the cosmic void at over 1 million miles per hour. You're on an incredible cosmic journey, moving through space-time at tremendous speeds, even though you feel perfectly still and at rest. And the space-time around you is not flat. It's curved, shaped by the presence of mass. Earth's mass creates a gentle curve in space-time, a depression in the four-dimensional fabric, and you're resting in that depression right now. This curvature is what we experience as gravity, what keeps you gently pressed against your bed, what holds the atmosphere close to the ground, what keeps everything on Earth's surface from floating off into space. The curve is subtle, gentle, not dramatically warped like space-time near a black hole or neutron star. But it's there, measurable and real, affecting how time passes for you and how objects move around you. Time is passing for you right now at a particular rate, determined by where you are in space-time and how you're moving through it. If you were higher up, farther from Earth's center, at the top of a tall mountain, or in an airplane, or on a space station, time would pass slightly faster for you. If you were deeper in Earth's gravitational field, down in a deep mine, or at the bottom of the ocean, time would pass slightly more slowly. But here, at this particular position in space-time, lying in your bed at whatever altitude you happen to be, time is flowing at exactly the rate you're experiencing it. Second by second, breath by breath, moment by moment, time is carrying you forward from past to future at a steady, comfortable pace. Take one more slow, deep breath. Feel how completely relaxed you are, how peaceful. We've explored so much tonight, from everyday experiences of space and time, to Einstein's revolutionary discoveries about their true nature. We've learned that they're not separate, not absolute, not the simple stage we once thought they were. We've discovered that they're woven together into spacetime, a flexible four-dimensional fabric that curves around mass and changes with motion. Einstein's discoveries opened up entirely new ways of understanding the universe. They led to predictions that seemed impossible, but turned out to be true. Black holes, where space-time curves so severely that nothing can escape. Gravitational waves, ripples in space-time itself, spreading across the cosmos. Time dilation near massive objects. All of these strange consequences of flexible space-time have been observed and confirmed. But Einstein's relativity, as revolutionary as it was, only tells us how space-time behaves. It describes the rules space-time follows, the ways it curves and flexes, and responds to matter and energy. It doesn't tell us what space-time actually is. What is this fabric made of? Where does it come from? Is it fundamental, or is it made of something even more basic, something deeper that we haven't discovered yet? These are questions that scientists are still exploring, still trying to answer, and they lead us into even stranger territory, into ideas about the nature of reality that challenge our understanding even more than relativity did. Ideas about the beginning of time, about whether space-time is made of tiny pieces, about whether space and time might not even be real in the way we think they are. Your breathing is so slow now, so peaceful and natural. Your body is heavy and still, completely relaxed. You're floating on the very edge of sleep, drifting gently through these cosmic thoughts. Your breathing is so slow now, so peaceful and natural. Your body is heavy and still, completely relaxed. You're floating on the very edge of sleep, drifting gently through these cosmic thoughts. And we're going to continue our journey, going to explore these deeper mysteries together. But we're going to pause here for just a moment. Just rest. Just breathe. Just let yourself sink a little deeper into the comfort and peace you're feeling. The universe is vast and strange and full of wonders. Space-time is more mysterious than we ever imagined, and there's so much more to discover, so many more questions to explore. But first, rest here. The journey continues soon. More mysteries await. But for now, just peace, just quiet. Just the soft embrace of deep relaxation. Breathe slowly. Feel how calm you are. And when you're ready, we'll continue exploring together, diving deeper into the nature of space and time, into questions about beginnings and endings, about the smallest scales and the largest, about what might lie beneath the fabric of space-time itself. Rest now, traveler. More wonders are coming, but this moment is for peace. So here we are, having discovered that space and time are not what they seemed. They're not separate, unchanging, absolute. They're woven together into space-time, a flexible fabric that bends and curves and responds to the presence of mass and energy. Einstein showed us this, gave us the mathematics to describe it, revealed a universe far stranger and more wonderful than anyone had imagined. But knowing how space-time behaves doesn't answer the deeper question. What is it? What is this fabric actually made of? Is it a fundamental aspect of reality, something that simply exists as a basic building block of the universe? Or is it constructed from something else, something smaller or more fundamental that we haven't yet discovered? And there's an even more profound question lurking beneath these. Is space-time even real? Or could it be an illusion, an emergent phenomenon that appears to exist but is actually constructed by our minds from something completely different. These questions take us to the frontiers of modern physics, to ideas that are still being explored and debated, to mysteries that remain unsolved. And as we explore them together, you're going to continue relaxing deeper and deeper, letting these thoughts carry you gently towards sleep. Take a slow breath. Notice how peaceful you feel, how calm. Your body is so relaxed now, so heavy and still. Your mind is drifting gently, engaged but not strained, curious but not tense. Just let these ideas flow through you like a gentle stream. Let's start with a question about the beginning. If space-time is the fabric of reality, the stage on which everything plays out, where did it come from? Has it always existed, stretching infinitely into the past? Or did it have a beginning, a moment when it came into existence? According to our best current understanding, space-time had a beginning. It started in an event we call the Big Bang about 13 billion years ago. Before the Big Bang, there was no space, no time, no space-time fabric. And then in an instant that's difficult to even describe because time itself didn't exist yet, space-time began. The Big Bang wasn't an explosion in space. It was an explosion of space itself. Space didn't exist before the Big Bang and then suddenly appear inside some pre-existing container. Space itself came into being, and as it did, time began flowing. In the earliest moments after the Big Bang, the universe was incredibly small, far smaller than an atom, containing all the energy that would eventually become all the galaxies and stars and planets we see today. And this tiny universe was expanding, not into anything external, but expanding in the sense that space itself was growing, stretching, creating more distance between points. And it's still expanding today. The universe is getting larger, not because galaxies are moving through a pre-existing space, but because space itself is stretching. New space is constantly being created between galaxies, pushing them apart, making the distances between them grow over time. This is hard to visualize because we're used to thinking of space as a fixed container. But space is dynamic, flexible, capable of growth. Imagine the surface of a balloon with dots drawn on it representing galaxies. As you inflate the balloon, the surface stretches and the dots move apart, not because they're moving across the surface, but because the surface itself is expanding. That's similar to what's happening with space in our universe, except instead of a two-dimensional surface, it's three-dimensional space that's expanding. And this expansion has been going on since the Big Bang, carrying galaxies apart, making the universe larger and larger over billions of years. We can observe this expansion by looking at distant galaxies and measuring how fast they're moving away from us. The farther away a galaxy is, the faster it's receding, exactly as we'd expect if space itself is expanding. Your breathing is so slow and peaceful. Feel how relaxed you are, how comfortable. We're thinking about the birth of the universe, about space-time coming into existence, but you're not working hard to understand every detail. Just let the thoughts drift through your mind gently. The Big Bang raises profound questions. What caused it? Why did it happen? What, if anything, existed before it? These are questions that physics struggles to answer because our mathematics breaks down at the moment of the Big Bang itself. The temperatures were infinite, the densities were infinite, and infinity is usually a sign that our equations are being pushed beyond their limits. Some scientists think there might have been something before the Big Bang, perhaps another universe that collapsed, and then rebounded in the Big Bang, starting a new cycle. Others think time itself began at the Big Bang, making the question of what came before meaningless, because there was no before. Still others speculate about quantum effects that might have triggered the Big Bang, or about multiple universes existing in some larger structure. We don't know for certain. The beginning of space-time remains one of the deepest mysteries in all of science. But let's move forward in time, away from the beginning, and think about what space-time is made of at the smallest scales. Einstein's relativity describes space-time as smooth and continuous, like a rubber sheet that can be bent, but has no texture or grain at the smallest level. But is this really true? Or might space-time, when you zoom in far enough, turn out to be grainy, made of discrete pieces like pixels on a screen? Some physicists think space-time might indeed be grainy at the smallest scales. They suggest there might be a smallest possible length, a fundamental unit of space that can't be divided any further. And there might be a smallest possible duration, a fundamental unit of time, a quantum of time that ticks away in discrete steps rather than flowing smoothly. These hypothetical smallest units are called Planck length and Planck time, named after the physicist who first calculated them. The Planck length is extraordinarily small, far smaller than an atom, smaller than any particle we've ever detected. And the Planck time is correspondingly short, the time it would take light to cross one Planck length. At these incredibly tiny scales, space-time might not be smooth. It might be bumpy, foamy, made of discrete chunks that can't be subdivided. Like a photograph that looks smooth from far away, but reveals individual pixels when you zoom in close enough, space-time might appear continuous at the scales we can observe, but become pixelated at the Planck scale. This idea comes from attempts to combine Einstein's relativity with quantum mechanics, the other great pillar of modern physics. Relativity describes gravity and the behavior of space-time. Quantum mechanics describes the behavior of particles and fields at very small scales. Both theories are incredibly successful, among the most accurate and well-tested theories in all of science. But they don't fit together easily. Quantum mechanics treats space-time as a fixed background, a stage on which quantum phenomena play out. Relativity treats space-time as dynamic and flexible, shaped by mass and energy. When you try to combine these views, when you try to describe gravity using quantum mechanics or describe quantum phenomena in curved space-time, you run into mathematical difficulties. The equations produce infinities and nonsensical results. Physicists have been working on this problem for decades, trying to develop a theory of quantum gravity that successfully merges relativity and quantum mechanics into a single consistent framework. And many of these attempts suggest that space-time at the smallest scales must be quantized, broken up into discrete pieces. One approach, called loop quantum gravity, imagines space-time as a kind of fabric woven from loops and nodes at the Planck scale. These loops connect to form a network, and the properties of this network give rise to the smooth space-time we experience at larger scales. It's like how a piece of cloth appears smooth from a distance but is actually woven from individual threads when you look closely. Another approach, string theory, suggests that the fundamental constituents of reality are not particles, but tiny vibrating strings of energy. These strings exist in a space-time that has more dimensions than the 3 spatial dimensions and 1 time dimension we experience. String theory proposes that there might be 10 or even 11 total dimensions, with the extra dimensions curled up so small that we can't detect them. In string theory, spacetime emerges from the behavior of these strings and the extra dimensions they vibrate in. Spacetime is not fundamental, but is constructed from something deeper, the strings and the higher dimensional space they inhabit. These are speculative ideas, theories that are still being developed and tested. We don't know yet whether spacetime is really grainy at small scales, whether there are extra dimensions, whether strings or loops or something else entirely are the fundamental constituents of reality. These questions remain at the frontiers of physics, puzzles that scientists are working to solve. Take another slow breath. Feel how peaceful you are, how deeply relaxed. Your body is so heavy now, sinking into the bed. Your mind is calm and quiet, drifting through these ideas without strain or effort. You don't need to understand every detail, don't need to grasp all the mathematics. Just let the thoughts flow through you gently. There's an even stranger possibility that some physicists are exploring. What if spacetime isn't real at all? What if space and time are not fundamental aspects of reality, but are instead emergent phenomena, things that appear to exist, but are actually constructed by our minds from something completely different? This might sound absurd at first. Space and time seem so obviously real, so fundamental to our experience. How could they be illusions? But consider other things that seem real but are actually emergent. Temperature, for example. When you touch something warm, you feel heat. Temperature seems like a fundamental property, but at the microscopic level, temperature doesn't exist as a separate thing. It's just the average motion of atoms. Fast-moving atoms create high temperature. Slow-moving atoms create low temperature. Temperature emerges from the collective behavior of many atoms, but it's not a fundamental property of any individual atom. Similarly, the concepts of solid and liquid and gas seem fundamental, but at the atomic level, these distinctions don't exist. There are just atoms interacting with each other in different ways. The macroscopic properties we call solid or liquid emerge from the collective behavior of countless atoms. Could space and time be like this? Could they be emergent properties that arise from something more fundamental, something that doesn't itself have spatial or temporal characteristics? Some physicists think this might be the case. They suggest that at the deepest level, reality might consist of information, of relationships between abstract entities that don't exist in space or time. And from these relationships, from the way this information is organized and processed, the appearance of space and time emerges. It's a bit like how the image on a computer screen emerges from the processing of digital information. The screen appears to show a two-dimensional space with objects in it, but really there's no space inside the computer. There's just information being processed, electrical signals moving through circuits, and the appearance of space emerges from this processing. Could our experience of three-dimensional space and flowing time be similar? Could reality at its deepest level be non-spatial and non-temporal, with space and time emerging only at larger scales, only for beings like us who are made of many particles and experience reality in a particular way? This idea is called emergent spacetime, and it's one of the most radical proposals in modern physics. It suggests that we're fundamentally confused about the nature of reality, that we're mistaking an emergent phenomenon for something fundamental, like ancient people who thought fire was an element rather than a chemical reaction. If this is true, then asking what space is made of is like asking what temperature is made of. It's the wrong question because space isn't made of anything. It's an emergent property, a way of describing relationships in a deeper reality that we don't yet fully understand. We don't know if this is correct. It's a speculative idea, a possibility being explored mathematically and philosophically. But it's a reminder that even the most basic things we take for granted, even space and time themselves, might not be what they seem. Your breathing is barely noticeable now, so slow and gentle. You're floating in that peaceful space between waking and sleeping, carried along by these strange ideas, these possibilities about the nature of reality. Don't try to hold on to anything. Just let it all flow through you. Let's think about time in particular, because time has some especially puzzling features. One of the strangest is that time seems to have a direction. It flows from past to future, never the other way around. We remember the past, but not the future. We can affect the future, but not the past. Causes come before effects, never after. Time's arrow points in one direction. But why? The fundamental laws of physics, the equations that describe how particles and fields behave, don't distinguish between past and future. They work equally well running forward or backward in time. If you filmed particles interacting and played the film backward, the backward version would still obey all the laws of physics. There's nothing in the fundamental laws that says time must flow from past to future. And yet, in our experience, time clearly has a direction. Eggs break but don't spontaneously reassemble. Coffee cools down but doesn't spontaneously heat up. We age in one direction, growing older, never younger. The universe as a whole is evolving from a hot, dense state toward a cold, sparse state, from order toward disorder. This directionality is connected to something called entropy, a measure of disorder or randomness. The second law of thermodynamics says that entropy tends to increase over time. Things tend to become more disordered, more random, more spread out. And this tendency gives time its arrow, its direction from past to future. But why does entropy increase? If the fundamental laws don't distinguish between past and future, why does the universe evolve in one direction rather than the other? The answer seems to be related to the initial conditions of the universe, to the state things were in right after the Big Bang. The early universe was in a very low entropy state, very ordered and organized, despite being hot and dense. And since then, entropy has been increasing, disorder has been spreading, and this increase gives us the arrow of time. But this just pushes the mystery back one step. Why was the early universe in such a low entropy state? What made the Big Bang special in this way? We don't have a complete answer. The initial conditions of the universe remain mysterious. Some physicists speculate that there might be regions of the universe, or other universes entirely, where time flows in different directions, where entropy decreases instead of increases. In those regions, if they exist, intelligent beings would experience time flowing the opposite way from us, though they'd still perceive it as flowing from past to future, because that's how consciousness works. It's a strange thought. Time might not have an inherent direction. The direction we experience might be a consequence of the particular region of reality we inhabit, the particular initial conditions our universe happened to have. Take a slow breath. Feel how calm you are. We're thinking about deep mysteries, about the flow of time and the nature of reality, but you're not struggling with these ideas. They're just passing through your mind gently, like clouds passing across the sky. Another puzzle about time is whether time travel is possible. Could you travel to the past or to the future, moving through time the way you move through space? Traveling to the future, in a sense, is easy. We're all doing it right now, moving forward through time at the rate of 1 second per second. But what if you wanted to move faster through time, to jump ahead to the future without experiencing all the moments in between? Einstein's relativity shows that this is possible. If you move very fast, time passes more slowly for you than for people who remain stationary. So if you travel on a fast spaceship for what feels like a few years to you, you might return to Earth to find that decades have passed. You've traveled to Earth's future, skipping over the intervening years. This is time travel to the future, and it's perfectly allowed by the laws of physics. It's not practical with our current technology because we can't accelerate to speeds close to light speed, but in principle it works. You could visit the far future of Earth, see what civilization has become, explore a world centuries or millennia ahead of your own time. But what about traveling to the past? Could you go backward in time, visit earlier eras, change events that have already happened? This is much more problematic. The laws of physics don't obviously forbid it, and Einstein's equations actually allow for spacetimes where closed loops in time exist, where you could travel around a loop and arrive back at an earlier moment. But whether such spacetimes can actually exist in nature, whether they're more than mathematical curiosities, remains unclear. Time travel to the past creates paradoxes. If you traveled back and prevented your own birth, what would happen? You'd never be born, so you'd never travel back, so you wouldn't prevent your birth, so you would be born, so you would travel back, and so on in an endless loop of contradictions. Some physicists suggest that the universe might protect itself from paradoxes by making time travel to the past impossible through some mechanism we don't yet understand. Others suggest that paradoxes might be avoided by multiple timelines or parallel universes branching off whenever someone travels to the past. We don't know. Time travel to the past remains in the realm of speculation, a fascinating possibility that might or might not be permitted by the true deep laws of physics. But even if time travel to the past is impossible, the fact that we can even discuss it seriously, that it's not obviously forbidden by everything we know, tells us something profound about time. Time is not the simple, obvious, one-way flow we thought it was. It's stranger and more flexible and more mysterious than everyday experience suggests. Your breathing is so peaceful now. Your body is completely still, heavy, and relaxed. You're drifting deeper into sleep, carried along by these thoughts about time and space and the nature of reality. Let's come back to where we started, to the simple, everyday experience of space and time. You're lying in bed, occupying a position in space, experiencing this moment in time. And we've learned that these simple experiences hide incredible depths. Space is not empty nothingness. It's part of space-time, a dynamic fabric that curves and flexes. Time is not a universal river flowing the same for everyone. It's flexible, passing at different rates depending on motion and gravity. Space and time are woven together, inseparable aspects of a four-dimensional reality. And beneath even this understanding, there are deeper mysteries. Space-time might be made of tiny quantum pieces at the smallest scales. It might emerge from something more fundamental. It might not be fundamental at all, but rather a way our minds organize experiences of a deeper reality. The universe began in the Big Bang, space-time coming into existence in that first moment and expanding ever since. and the universe might end someday, though how and when remains uncertain. Space might expand forever, growing colder and emptier, or it might eventually contract, collapsing back into a tiny, dense state similar to where it began. We don't know the ultimate fate of space-time, just as we don't know its ultimate nature. These are questions at the frontiers of human knowledge, puzzles we're still working to solve. But even without complete answers, even with mysteries remaining, we've learned something profound. Reality is not what it appears to be on the surface. Space and time, which seem so obvious and simple, are actually deep and complex and strange. The universe is more wonderful and more mysterious than our everyday experience suggests. And you're part of this mysterious universe. You're embedded in space-time, moving through it, experiencing it. The atoms in your body are made of particles that obey quantum laws and gravitational laws that move through curved space-time that are connected to everything else in the universe through the shared fabric of reality. You're not separate from the cosmos. You're woven into it, a temporary pattern of matter and energy that has become conscious, that can think and wonder and ask questions about the nature of existence. And right now, that conscious pattern is preparing for sleep. Your body is ready, your mind is quiet. You've wandered through cosmic mysteries, explored the nature of space and time, thought about beginnings and endings and the fundamental structure of reality. But now it's time to let all of that go, to release these thoughts and drift into the peaceful darkness of sleep. Take one last slow breath. Feel how completely relaxed you are, how heavy and still. Your body is sinking into the bed as if the mattress is gently embracing you. Your mind is calm and empty, ready to release everything and rest. The universe is vast and strange and beautiful. Space and time are more mysterious than we ever imagined. Reality at its deepest level remains unknown, a puzzle we're still working to solve. But these mysteries don't need to be solved tonight. They'll still be there tomorrow, waiting for curious minds to explore them. Tonight is for rest, for sleep, for letting go of everything and drifting into peaceful unconsciousness. You've traveled far in your imagination tonight, from everyday experiences to Einstein's insights to the frontiers of modern physics. You've thought about flexible time and curved space, about quantum gravity and emergent reality, about the beginning of the universe and the nature of time's arrow. It's been quite a journey, and now the journey is complete, at least for tonight. Rest now. Let your mind go quiet. Let your thoughts dissolve like mist evaporating in morning sunlight. You don't need to think anymore. Don't need to wonder or question or try to understand. Just rest. Space and time will continue their dance. The universe will keep evolving. Space-time will keep expanding and curving and rippling. But you don't need to think about any of that now. Just sleep. Feel how peaceful you are. How calm, how ready for deep, restful sleep. Your body knows what to do. Your mind knows how to let go. You've done this countless times before, drifting off to sleep, releasing consciousness, allowing your body to rest and recover. Tonight is no different. Sleep is here, waiting for you, ready to embrace you gently. All you have to do is let go. Release your thoughts. Release your awareness. Release everything and drift into the soft, welcoming darkness. You are floating through space-time, but you don't need to think about that. You are part of the cosmic dance, but you don't need to ponder it. You are a temporary pattern of consciousness in an ancient and mysterious universe, but none of that matters right now. Right now, there's only sleep, only rest, only the gentle descent into unconsciousness where dreams may come or may not, where time passes without your awareness, where your body and mind can recover from the day. Sleep now, deeply and peacefully. Let go completely. Release everything. The mysteries of space and time will wait. The universe will wait. Everything will wait while you sleep. Good night, traveler. Good night, cosmic explorer. Good night, consciousness drifting gently away. Sleep well. Sleep deep, sleep peacefully. You are safe. You are at rest. You are exactly where you should be. Good night. Our story ends here. If you're still awake and would like to stay with us in future content, don't forget to subscribe to the channel. And if it's already late, I simply wish you a peaceful night's sleep. The brown noise you're about to hear is a low-frequency, steady sound designed to help calm your mind and relax you as you sleep. Good night.